Mr. Bell Physics! Hello, and welcome back to another exciting episode of Mr. Bell Physics, and I hope that you guys like the new intro. That is courtesy of one of my students. Thank you very much to that unnamed student for legal reasons. But I'm sure it looks great. Today, per a request from one of the commenters here, we're going to be covering something that's outside of my curriculum for how we teach our physics course here at the high school that I work at. Instead, we're going to be covering something called uniform circular motion. Now, circular motion is a lot like regular motion, i.e. kinematics. So to understand the basics of kinematics, I would refer you to that playlist, which is on the channel already, has, I believe, 6 parts to it. Goes through plenty of different examples of how to get used to working with kinematics and how to be comfortable with kinematics, because a lot of those ideas are going to carry over here as well. Now, the big difference between kinematics and uniform circular motion is that instead of going in a straight line, we are now going in a circle. But we can actually convert between the two of them. See, if you really think about this, right, and you can ignore this table for now, just kind of pay attention down here for a second. And we have a thing that's moving like this, right, over time, going in a circle. If we instantaneously stopped for a second and recorded what its motion was, it would actually be a straight line. See, kinematics and uniform circular motion are very related to each other. And what we'll find out is that a lot of the equations are just pretty much the exact same thing, but just with new letters. So let's talk about that. Now, we call regular kinematics tangential movement here. The reason why it actually goes all the way back to like calculus and stuff like that, technically this straight line is called the tangent line, or dealing with a curve. In tangential motion, i.e. straight motion, what you're already used to, you're used to displacement being represented by x or maybe a delta x, velocity being v, and acceleration being a. Right, where this is in meters, velocity is in meters per second, and acceleration is in meters per second squared. Nothing too crazy there. Angular motion changes some of these. Displacement, velocity, and acceleration are all still values in uniform circular motion, in any sort of rotational motion, right? We're still moving here after all. We are still moving at a velocity that can be measured, and we are still changing that velocity, so therefore we need an acceleration. However, we represent them using different variables. Instead of delta x, or just x, we use the Greek letter theta, or delta theta. The reason why is because what we're really measuring is if we start, say, here, and we end up here, it's more useful for me to understand what that angle is down there than it is to necessarily know the arc length. Because I can be any distance away that I want to be from the center of the circle. Either way, the angle doesn't change. And that angle is measured in a unit called a radian, not degrees. Okay, we'll talk about what a radian is and how to convert between them and degrees momentarily. Velocity, instead of v, we use the lowercase Greek letter omega, which kind of looks like a bit of a curvier W, I guess you could call it. And like how velocity is measured in meters per second, or unit of displacement per second, angular velocity is measured in radians per second. So radians per second. Now, for acceleration, instead of a, we also use a Greek letter here. We use the Greek letter alpha, which looks like that. It looks pretty similar to an A, but it is different. And we measure this like tangential acceleration is meters per second squared. You could probably take a guess as to what angular acceleration is going to be. We're going to do the whole Dora the Explorer thing. What do you think is going to be? Wow! Or, oh, I don't know what you said. Radians per second squared. So radians per second squared. Now, with this in mind, whenever I'm referring to velocity, acceleration, or displacement in uniform circular motion, I'm usually talking about the angular variance of them. But I still had to be careful to mention that I'm talking about the angular variance because we can easily convert between the two of these. And again, we will talk about that in this episode as well. So, first things first that I think is important to address with this is what is a radian, right? I know when I took physics for the first time and we were introduced to this, I had no idea what a radian was. So, let's start with that. Then we'll start talking about how he used these in equations and stuff like that, and then we can talk about how we convert between the two, and that'll be our video for today. So expect a bit of a longer one here, kind of cramming a few videos into one, just to have one nice, neat upload for the entire kind of rotational motion unit done. So let's erase this table, okay? Hopefully you have this written down by now. But erasing this, let's say we have a circle. Like that. Okay? Well, at least that's my best attempt at one. Now, if we think about this like an XY coordinate plane, we're used to dealing with angles in degrees. So if this is 0 degrees, we're used to this being 90, 180, 270, and then back here to 360. That's what we're generally used to. But all a radian is a different way of measuring an angle. And the reason why we use radians is because this is what the math works out in. Technically speaking, radians are more precise than degrees. See, with degrees, we only have 360 individual kind of notches here, right? And we're using whole numbers at least. If we start breaking down in decimals, we get a little bit more specific than that. But with radians, radians are dependent on pi, which for a circle makes things much, much more precise. The general rule is that, and I'm going to write it right over here, 360 degrees equals 2 pi radians. Okay, this is the big one. 360 degrees, or one full rotation, is equal to 2 pi radians. So, this will be 0 radians. This will be 2 pi radians. Alternatively, this also means 180 degrees is equal to 1 pi radians. Now, of course, pi is about 3.14. It's an irrational number. It has no specific end. This is why we have a pi button on most calculators nowadays. We express radians in terms of pi to make it a little bit easier to write, okay? In actuality, yes, it's like 2 times 3.14, so about 6.2-ish radians per full revolution. That is correct. But by expressing it in pi, we get a much more precise value. So instead of 180, this becomes pi radians. Instead of 90 degrees, we get 1/2 pi radians. Instead of 270, we get 1.5 pi radians. So when we're doing our unit conversions, which we'll do a basic one here, we can convert from radians all the way into degrees or revolutions. depending on what we want to do. Okay. So let's say hypothetically, okay, I'll erase kind of this part of the circle here. Let's say hypothetically I have 5 pi radians, right? Is my given angular displacement. And I want to convert that both into degrees, but also into revolutions. So I want to know how far in degrees did this thing actually move angularly, and also how many times did it actually spin. So let's do that conversion real quick. So we start off with our given information, 5 pi radians. Put it over 1. I know for a fact that 2 pi radians is equal to 360 degrees. You could also use pi radians is 180 degrees here. The math will come out exactly the same. I know that I want to be in degrees at the end, so I know that I'm all good. Cancel out my radians. Find my calculator. It's over there on my desk. Hit some numbers. So we get 5 pi times 360 divided by 2 pi. And I just want to make sure that I'm doing this right here. Because what we should get is essentially, if 2 pi is one full rotation, we should have 2.5 rotations here. Right, so it should be equal to this 360 times 2.5, which is 900. So we want to make sure that we're doing this right in our calculator, right? Since I have pi on top and on bottom, I can actually just get rid of it. They cancel out. So 5 times 360 divided by 2 comes out to be 900 degrees. Awesome. Same exact idea here. Start with 5 pi radians. Put it over 1. I know 2 pi radians is 1 revolution. My radians cancel out. My pi's also cancel out. So I do 5 divided by 2, and I get 2.5. Bada bing, bada boom. So now that we know how radians actually work, now we can actually put them to use. What I have here on the board is a series of equations, as you can see. In blue here, I have our standard kinematic equations that we've been used to using. Okay, these are tangential equations. These measure in straight lines. And they're written out in the same order as usual. Okay, V final equals V initial plus acceleration times time. Okay, V final squared equals V initial squared plus 2 times acceleration times displacement, so on and so forth. The thing is, again, the angular values of all these work in the exact same way as the tangential values of these things, just with different units. So for example, if you want to solve for angular velocity, all you need is your change in angular position, or your displacement, and your time, do displacement divided by time. If you want your angular acceleration, sorry, that shouldn't be an A, that should be an alpha, my bad. The difference is important here. All you need to do to find angular acceleration is do your angular velocity divided by your time. It's the exact same thing as it was before. Remember, finding regular velocity is just doing delta x divided by t. Finding regular acceleration is just doing change in velocity divided by time. All this is, our equation before was v final minus v initial divided by t. Now it's omega final minus omega initial divided by t. That's the only difference. The math is the same, and that applies to the actual kinematic equations as well. When we have a constant angular acceleration, the equations are the exact same, just with our new variables. Instead of it being v final equals v initial plus acceleration times time, now it's omega final equals omega initial plus angular acceleration times time. So solving out a problem for uniform circular motion and for rotational motion in general, so long as you have a constant angular acceleration, is the exact same as solving a kinematics problem. The only difference is that usually you may want to know how many revolutions or rotations something has done, which you now know how to do because you know what a radian is. Ultimately, even though the letters look a lot more funky, to put things lightly, they aren't anything to be more scared of. They're the exact same math as before. So, if we were to do an example problem, let's say, hypothetically, right, I'm just going to make up some numbers here. But let's say, hypothetically, I'm going to actually get rid of our tangential equations for this. Let's say I start from rest, so initial velocity is 0. I thought I was going to sneeze there. I did not. So initial velocity is 0 radians per second. And then let's say we have an angular acceleration of 5 radians per second squared, which is pretty fast. Let's say I wanted to know how long would it take me to get to a final velocity, angular velocity that is. I'm just going to pull a random number here. 1,130 radians per second, sure. It's like 11:30 at the time of me recording this. So when we do this math out, okay, we're going to be solving for time here. I'm immediately going to want to look at my equations, see what I have, see what I don't have, right? I have initial velocity, final velocity, acceleration. I'm solving for time. I want an equation that has all 4 of those. And again, generally, I like going in this order because it usually makes things easier to solve. Top equation has final, has initial, has acceleration. Looking for time. We have everything we need here. We can plug in and we can solve. So let's go ahead and try this. So, omega final, 1130, equals omega initial, 0, plus acceleration, 5, times time. So, the 0 goes away because it's 0, it doesn't do anything. And I can divide both sides by 5 to get t by itself. The reason why I'm doing that is because 5 is multiplying t right now. I want t by itself, so I have to undo that multiplication. The only way to undo multiplication is to do the opposite of it, which is division. And as with anything in algebra, what I do on one side, I must do on the other side as well. So in a calculator, I'm going to do 1130 divided by 5. And I get t is equal to 226 seconds. I'm actually surprised that came out to be a whole number. So that means that if this thing is speeding up at that angular momentum for this long, it will hit this speed. But it will take a while to do that, obviously. 3 minutes is 180 seconds. So this is bordering on 4 minutes. So it's going to take a little while. But that's not necessarily shocking. Now let's say instead, we want to know how much distance it's going to cover in that amount of time. So I now know that t is 226. Let's say I want to know theta. So to solve for theta here, we don't necessarily even need final velocity. See, there's a few equations that we can use here to solve for theta, and they will all give us the exact same answer. This second equation, if we had final velocity, initial velocity, and acceleration, would give it to us. Or this equation right here, if we have initial velocity, time, and acceleration, will give it to us. I feel like using this one, just because I haven't used it in a minute. So let's solve for what our angular displacement will be. Mind you, this is going to give us a number of radians, not in terms of pi. If you want to make it in terms of pi, you must then divide your final answer by pi. I'll show you how to do that in a minute. So, theta equals initial velocity, 0, times time, 226, plus 1/2 angular acceleration, 5, times t, 226, squared. Immediately, 0 times 226 cancels out because any number times 0 is 0. And 0 doesn't do anything for me. So that goes away immediately. Which leaves me with this little thing to simplify here. Let's do 226 squared first. I do that and I get 51,076. So, 51,076 times 5 comes out to be 255,380 divided by 2 comes out to be a rather large number of delta theta equals 127,690 radians. Again, this is not in terms of pi. If I want to make it in terms of pi, I must divide that number by pi. And when I do that, I get an alternate answer of 40,644.98 pi. Both of those are acceptable answers. All right, final bit. How do we go from tangential acceleration or velocity to their angular counterparts and vice versa? And also, how does this also get applied elsewhere in physics? Let's start off with the second question first. Now, you may have heard of this term called centrifugal force before. Now, as a quick little demonstration, I have here a rather large container filled with a bunch of lollipops, right? If I dump the container out, lollipops fall, right? Now, that's the case unless I rotate this thing rather quickly, like so. Even though I did that, all of the lollipops stay practically glued to the bottom of my container here. Now, the reason why that is happening is because a force is being applied by the lollipop. Or not by the lollipops, but rather on the lollipops by me. Since I'm rotating it around, an acceleration is pointed towards the outside of that circle. And that creates a force because that object has mass. We call that centrifugal acceleration, or centrifugal force. And we find it by doing mass times our rotational acceleration. We can also do it by doing mass times velocity squared divided by the radius of our circle. So just to remind you what a radius is, say we have a circle. That circle is going to have a center point. The imaginary line from any point on that circle to that center point is our radius and is always the same distance. Okay? So we use r to label that. And r is constant throughout a circle. That's kind of what a circle is. Now, to go from angular velocity to tangential velocity, all we need to do is take our angular velocity and multiply that number by our radius in meters. Okay? So r must be in meters. Very, very important. Now, this will give us a velocity in meters per second. Same exact thing applies for angular acceleration going to tangential acceleration. Multiply that value by the radius in meters, and you get the tangential version. Similarly, these equations can be rearranged. Instead of solving for tangential values, let's say I want to solve for the angular values. All I have to do instead is divide both sides by radius. So I'm left with angular velocity is equal to tangential velocity divided by r, and that angular acceleration is equal to tangential acceleration divided by r. With that being said, these are pretty much all of the basics that you need to know for uniform circular motion and rotational motion in general. The entire unit is essentially a repeat of kinematics. If you've done kinematics and you feel comfortable with kinematics, you're almost guaranteed to feel comfortable with this. It's just a minor shift in perspective. Instead of going in a straight line, we're going in a circle instead. So it's just a matter of changing your perspective, which is something that we have to be good about in physics quite often. See, being able to visualize things from different perspectives in physics is very, very important. This is kind of the introductory example of that. So, hopefully this helps you out. Hopefully this makes you feel a little bit better about it. I will admit it has been a little while since I've done this physics or done this math. So, I hope that for whatever it was worth, it was helpful. So, with that all being said, I'd like to thank you so much for watching. I want to remind you to absolutely smash that like button. Make sure you ring the bell once you subscribe for notifications for whenever this channel uploads with a brand new physics video. And as always, I will see you in the next video. Have a good one.